Okay, now that we're done talking about sequences, let's talk about series. And again, this will be a little bit of a review. Okay, but a series is going to be a sequence of the form a sub n is going to be b sub k as k goes from, say, 1 to n or 0 to n, or it doesn't really matter. Say it goes from j to n, doesn't matter. So a sequence here is a series. Okay, and sometimes this is called the series of partial sums of b sub k. Okay, so b sub k is called the sequence of terms. So sequence of terms. And a sub n is called the nth partial sum of the sequence b sub k. Okay, so this is a little bit of review, but I guess there's a little bit new here in that we have not previously ever thought about sequences that have complex values. So remember that we're still talking about complex valued sequences, even though just before when we talked about the monotone convergence theorem, we were talking about real valued sequences. But I think that was the only place where we needed to have a real valued sequence. Everything else is true for sequences in complex, for sequences with complex values. So that's a series in general. A series converges to L. So a series converges to L if the sequence of partial sums converge to L. So in other words, if the limit of a sub n is L. And so what this means is that if you were to have a series, so the way that this often gets used is that if you were to have a series b sub k, you could think of this as the limit, just kind of like when you're doing improper integration in Calc 2, you could think of this as the limit of the partial sums b sub k. And then we're saying that that is, if that limit is L, so in other words, this is the limit of the partial sums. And then if those go to L, we say that the original series converges to L. Okay, and so just a few common series and a few common tricks with series. Again, this is a little bit of review, but if the modulus of z is less than 1, then 1 over 1 minus z is going to be the sequence z to the k as k goes from 0 to infinity. You're probably used to thinking about this if x is between -1 and 1, then we have this. This is the standard geometric series. And now we're going to actually learn why in Calc 2 these are called the radius of convergence. In the, in Calc 2 they're actually called, it's the interval of convergence. But the fact that we're talking about a radius of convergence means that we're actually talking about circles here. Sorry, my iPad is dying. Yeah, this is true for all complex numbers that live inside the open disk centered at 0 of radius 1. So that's going to be true. And if, so just to follow up here, if the modulus of z is greater than or equal to 1, then this series diverges. Okay, so this series diverges. Okay, so if the modulus of z is greater than or equal to 1, the series diverges. Not really too much more to say there. The book, for whatever reason, really likes it when these series start at 1. So when you have the sum from 1 to infinity, this is really just the same as the sum from 0 to infinity minus what happens when k is 0. So minus z to the 0, which is 1. So this is going to end up being 1 over 1 minus z minus 1, which happens to be z over 1 minus z. Okay, so the book really likes this version. I think it's just nicer and cleaner to think about the sum starting at 0, and then everything else falls out right away. Okay, so that's yeah, geometric series in a nutshell. A few other things. If you were to have, say, the sum of 1 over k times k plus, pick whatever number you want, but let's say 2. And then we're going to look at the sum as k goes from 1 to infinity. This is going to end up being, well, when k is 1, you're going to get 1/2. when k is 2, how do I want to do this here? This is going to end up being, yeah, let's do partial fraction decomposition, because otherwise it'll be a little bit mysterious. But this is going to be 1/2. The sum goes from, let's see, this is going to be 1 over k minus the quantity 1 over k plus 2. So let's make sure I did that right. If you combine these, you get k plus 2 minus k divided by the product of the denominator. So that's 2, hence the 1/2 in front. So that's perfect. And so let's see, if you start plugging in terms, this is going to be 1/2. We're going to have 1 minus a third plus a half minus a fourth plus a third minus a fifth plus 1/4 minus 1/6, and so on. Okay, and so if you notice, all these terms are going to cancel. And importantly, not only do these terms cancel, but the terms also have to go to 0. And so the thirds are going to cancel, the fourths are going to cancel, this fifth would cancel with something over here eventually, probably the next thing I would have wrote, and so on. And so it turns out that everything is going to cancel except for the 1 and the 1/2. Okay, so the only terms that don't get canceled are that 1 and that 1/2, and therefore this entire series is going to converge to 1/2 times 3/2, so 3/4. Okay, so this entire series converges to 3/4. This is what's called telescoping. So this is a telescoping series. Telescoping meaning that some of the later terms cancel the earlier terms, and all the terms go to 0, because you get this nice convergence pattern. Okay, so you have to imagine the old like cartoony pirate telescope that like unfolds. That's the kind of telescope that they're talking about. Anyways, let's talk about the a few other things here. There's the comparison test. There's the divergence test. Let's start with the divergence test, because I think I forgot to write that down. So the divergence test basically says that if you have a series and the series converges, then the terms b sub k have to go to 0. In other words, if the terms b sub k do not go to 0, then the series diverges, no matter what. Okay, so then the series diverges. Okay, so this is called the divergence test. Now, basically all of the series that we're going to talk about, the terms will go to 0, but that doesn't tell you that it converges or not. All that we're saying is that if the terms don't go to 0, then it definitely diverges. Okay, but if it converges, the terms have to go to 0. Okay, so just be careful here. If the series converges, the terms go to 0. If the terms go to 0, the series may or may not converge. All we know for sure is that if the terms don't go to 0, it automatically diverges. But if the terms do go to 0, we just have more work to do. We just have to figure it out using everything that we know and that we'll talk about. The proof is really straightforward. Okay, so the proof here is that if you think about b sub k, this is going to be, well, you can think of this as the kth value. So you can think of this as the sum from 1. So let's call this the sum of b sub j as j goes from 1 to k, minus the sum as j goes from 1 to k minus 1. And then let k go to infinity. So if we look at the limit of b sub k, as k goes to infinity, this is going to be L minus L, because we're assuming that the series converges to some value L. And in particular, this value b sub k is going to go to 0. Okay, because both of these values are going to converge to L. Okay, so that's I don't want to call that exactly a proof, but that's the main idea in the proof. I don't think there's really any details that we need to worry about. All right. Next, let's talk about the comparison test. The comparison test is also an idea that's only relevant for real valued sequences. There is no comparison of less than or equal to or greater than or equal to for complex numbers. So what this comparison test says is that if, let's say we have two series with sequence of terms that follow an inequality. So let's say that here we have b sub k and c sub k. So if these are real valued, and if b sub k is less than or equal to c sub k for all k, then the following is true. If the sum of c sub k converges, then the other sum converges. The one that's less than or equal to that also converges. And on the other side, on the other hand, if the sum of b sub k diverges, so if the sum diverges, then the sum of c sub k, the larger one, also diverges. Okay. And yeah, that's the comparison test. I like to think about the comparison test, even though it's not exactly a legal way to write this. I like to think about this, that if b sub k is less than or equal to c sub k for all k, that implies that the sum of b sub k is less than or equal to the sum of c sub k. Okay, that's not, that doesn't actually make good sense, strictly speaking, because if the series are divergent, then we're talking about two infinities being less than or equal to each other. And you have to be a little bit careful here, but I think this kind of gets across the essence of what this statement, what this proposition says, right? If you have two sequence of terms and one's larger than the other, and if the larger series converges, then so does the smaller one. If the smaller series diverges, so does the larger one. Okay, so that's what, basically, that's what that says. Okay, here I forgot to add, oh no, I did it, that b sub k and c sub k are positive real valued sequences. So they're greater than or equal to 0. Okay, that part's important. The proof is very straightforward. I'll just give you the proof of 1. That'll give you the idea for the proof of 2. And again, this is going to be a little sketch. I'm going quickly because we have only a few weeks left, but also this is not really anything new. This is all stuff that you really learned in Calc 2, right? Math 1900. So now that we're in a 4,000 level math class, there's a few things that I'm taking for granted. So I'm just going a little quicker here. And probably proofs weren't emphasized in Calc 2. At least I don't emphasize proofs when I teach Calc 2. It's more about the application. So I do want to do a little bit of that, but the idea is really straightforward. So let's assume that 0 is less than or equal to b sub k, is less than or equal to c sub k for all k. And let's say that this sum, c sub k, converges to L. So converges to L. Then this sum, b sub k, has to also converge. And the reason is that b sub k, let me actually say it this way. Let's look at the sum a sub n, which is defined to be the sum of b sub k as k goes from 1 to n. This is monotone and bounded. Right? It's monotone because the b sub k's are greater than or equal to 0. So each of the values a sub n is greater than or equal to the previous value because we keep adding non-negative values. So this is monotone and bounded. Okay, it's monotone because a sub n plus 1 minus a sub n is equal to b sub n plus 1, which is greater than or equal to 0, because we're assuming all the terms are greater than or equal to 0. It's bounded. It's bounded because a sub n is less than or equal to L. I don't really have to say too much more here. The value a sub n is less than or equal to L for all n, because L is the limit here. Again, c sub k is positive, so that's going to be a value that's going to be continually increasing. This is going to converge to L. And if I wanted to write this out a little bit more in some more detail here, a sub n is equal to I'm cheating just slightly, sorry. But this is equal to the modulus of b sub k. So k goes from 1 to n. And then that's, actually, we don't even really need the greater than or equal to signs here, because everything is positive. And that's less than or equal to this sum, k goes from 1 to n, which is less than or equal to L, because again, C sub k is greater than or equal to 0, so this is going to converge by increasing to L. So A sub n is also bounded above by L. But there you go. So A sub n is a bounded monotone sequence, therefore it converges. Okay, so the monotone convergence theorem implies that A sub n converges. In other words, if the partial series converge, then the series converges. Okay, so that's, again, a quick sketch, but hopefully that gets the idea across. All right. Okay, so that's a comparison test. A few other tests that we talked about. There's the integral test. Okay, so there's the integral test. The integral test says, oh, by the way, I wanted to apply, I'm sorry, I wanted to do one example of the, whatever I just called it, a comparison test. So one example. So I want you to notice that, actually, there's two things I want to say here. Sorry, I need to backtrack just slightly. Everything I said is true, but you can say this a little bit stronger. Okay, so if b sub k and c sub k are real valued and satisfy this inequality for all k, then what I said is true. But actually, it's also true, and you'd have to modify the proof a little bit, but this would also be true if this inequality only holds for all sufficiently large values of k. So let's say that when k is at least 100, this inequality is true. Well, then the original series, then both of these statements are going to be true, right? If this sum of c sub k converges, then so does the sum of b sub k. And the way that you know that, if this is true for the first 100 terms, is that you first just take the first 100 terms and put them in a pile, and then you apply the convergence theorem to the rest for all the terms that are 100 or 1 or greater, and then everything works fine for the terms that are 100, 1 or greater, and then you can add back the finite number of terms that you had in a pile before. And so really, you don't need this to be true for all values k. You only need it to be true for all sufficiently large values of k. Okay, so as long as this is true for all values k greater than or equal to 10 or 1,000,000 or 5 or whatever, then the comparison test is true. So just to emphasize that, I wanted to do an example, and I want to think about this 1 over n factorial as n goes from 0 to infinity. Okay, so again, we proved that this converges, but I just want to kind of look at this a little bit and see how this works. 1 over n factorial, if we think about this, this is what? This is going to be 1 plus 1 over 1 factorial plus 1 over 2 factorial. This is 1 over 0 factorial. 1 over 3 factorial plus the rest. So here n goes from 0, I'm sorry, n goes from 4 to infinity. So 1 over n factorial. And so this is going to be, let's see, 1 plus a half plus a sixth, which I think we said before was 8/3. I think that sounds right. So that's 2.5 plus a sixth. A half plus a sixth is 2/3. So yeah, so this is 8/3 plus the rest. And what I'm going to do is I'm going to notice that, again, n factorial is greater than or equal to 2 to the n if n's at least 4. And so if I take 1 over n factorial, that'll be less than or equal to 1 over 2 to the n if n is at least 4. Okay, and so that's going to be the sum of 1 over 2 to the n as n goes from 4 to infinity. And this is going to be, let's see, now we just have to calculate what this is going to be. So 1 over 2 to the n, so 1 over 2 to the n, on the one hand is going to be 1 over 1 minus a half, which is 2. On the other hand, we're missing the first few terms. So this is just the sum starting at 0. So if we have the sum starting at 4 of 1 over 2 to the n, This is going to be the sum from 0 to infinity minus what happens at 0. So that would be 1, plus what happens at 1, what happens at 2, so it's 2 squared, plus what happens at 3. Okay, and so this is going to be 2 minus, let's see, 1 plus a half plus a fourth plus an eighth is going to be, so this is all over 8. So this is 1/8, 2/8, 4/8, and 8/8. So that's 15/8. And so if we have 2 minus that, that's going to be 1/8. Is that right? I think that's right. And so what this tells you is that this is less than or equal to 1 plus 1 plus a half plus a sixth plus 1/8. And in particular, it converges. So this is, now we have to do this again. I don't know why I make myself do this algebra, but here we are. So we have 6 and 8. So it looks like the least common multiple there is going to be 24. And so this is going to be, I'm just going to think of this as 5 halves plus 1/6 plus 1/8. And that is, let's think about this in terms of 24ths. So 5 halves is 60 24ths. 1/6 is 4 24ths. 1/8 is 3. So altogether, this is 67 over 24. And what this does is this gives us an upper bound on E. So 67 over 24 is 2.71, 2.79. Okay, so 2.7917. Okay, that's the idea. And of course, we know E is 2.718. And so this was a pretty crude bound. This inequality is like wildly ineffective because this inequality is true basically when it's only really a good inequality when n is small. When n is big, n factorial is way bigger. So 1 over n factorial is way smaller. But anyways, this kind of gives us another upper bound for E. So that's the kind of thing that we can do with these power series.